Okay, good afternoon. This is 16th lecture, and now we will start our discussion on spheres at high Reynolds numbers. Okay, typically here, whenever I am talking about the spheres, we can have both type of spheres, solid spheres as well as the fluid spheres. The only condition is that Reynolds numbers are high. In case the Reynolds numbers are high, we cannot avoid now the advection terms which are present in our governing equations. Okay, so because of this difficulty, now our governing equations actually becomes non-linear. So if you see particularly in the Navier-Stokes equation, the advection term is nothing but having non-linear nature. Okay, so because of this non-linearity and other challenges, finding the complete analytical solution of this type of problem is actually not at all possible. So complete analytical solution is not possible. So what we have to do, we have to go for some alternative approaches in order to determine the flow physics at high Reynolds numbers. So other approaches are, we know that one of the approach which is available is experimental approach, and second approach is simulation approach. Okay, so in case of numerical simulations, we can actually solve the set of governing equations, detailed set of governing equations using some simulation techniques. Okay, and the third approach, which is nothing but a kind of ad hoc approach. Okay, so in experiments and simulations, the difficulty is that if you have to do experiments, then you have to build setup, there will be some cost involved, and it will be a long cumbersome process. Similarly, in terms of simulations also, simulations take significant amount of computational resources and significant amount of time to reach the final solution. Okay, but the beauty with the analytical techniques is that if you know analytical solution, you can simply apply on your physical situation, and then you will quickly get some good estimate of the output parameters or flow parameters what you can have. So that's why though detailed analytical solution is not possible, but one simplified or approximate analytical solution is possible by considering the approximation of boundary layer. Okay, so if we consider the boundary layer approximation, particularly at high Reynolds number, so what we can do, we can divide our regime in between the boundary layer region, which will be a viscous regime, and then outside boundary layer region, which will be a inviscid regime. Okay, so basically what will be happening, any field variable which I will be calculating outside the equation, that can outside this boundary layer region, this can be calculated by simply applying the potential flow theory. Okay, so in terms of potential flow theory means here outside I can simply apply the Bernoulli's equation. So some parameters I can calculate outside, and then I can determine that what are the parameters which are having same value outside and inside the boundary layer. So if there are certain parameters which if I calculate outside the boundary layer, these will be having actually same value within the boundary layer also. So with transverse direction, these parameters will not be having any change. Okay, so if now I calculate some parameters outside boundary layer and then use these parameter as a known parameter inside the boundary layer, and within the boundary layer if I take some more assumptions to remove some of the terms which are creating complexity in the Navier-Stokes equations, then we will be getting simplified set of equations, and with this simplified set of equations actually we can find the approximate analytical solution. So why we are calling these solutions as approximate? Because we are not considering that all the terms which are present in the system, but we are actually neglecting some of the terms. So that's why what I will do, quickly first I will explain to you about the boundary layer approximations, and then we will move towards the and simulation approach, and then we will see what are the different outcomes if flow is actually happening at higher Reynolds number on different spherical particles. Okay, so we know that in case of boundary layer theory, what typically happens, so this is a plate, and this particular wedge section is having actually length L, and in this direction my x is increasing. Okay, so here you will be finding if your flow Reynolds number is very small, so Reynolds number of the flow is actually close to 10. So corresponding to this, you will be finding that at far away from this surface, you will be having uniform velocity. So that's why velocity value can be clearly written as u. And this Reynolds number, whatever I have calculated, this I have given subscript L. So the meaning is that length scale over here is nothing but considered equal to the length of the system. So rho u L by mu. Okay. And in this type of system, we know that because of the no slip boundary condition, what will be happening? We will be having here, if this solid surface is actually stagnant, so just close to surface I will be having zero velocity, and when I will be moving away from the surface, then my velocity will keep on increasing, and at certain point I will be having velocity close to 99% of the free stream velocity u. So this velocity away from the surface, this is called as actually free stream velocity. Is this point clear? So now what you have some variable velocity profile here, where velocity is actually varying in transverse direction, and outside this you have almost same value of the velocity. So it means within this you have the slow down of the flow because of the viscous dominance effects. So that's why I will be calling this region of the flow as viscous region, and outside this I will be calling the flow region as inviscid region. Okay, but one simple point is, whenever my Reynolds number is very very small, corresponding to that I will be finding that whatever this streamline which is moving out in the inviscid region, that have to actually bend through a very large portion. Okay, so it will be having large displacement because of the presence of this viscous dissipation within the system. Is this one clear? So this is one assumption. Then next we have very high Reynolds number. So in the previous case my Reynolds number was close to 10, and in the next case my Reynolds number is actually 10 to power 7. So extremely high Reynolds number. So in this scenario, if you see, your boundary layer thickness is actually very very small. Okay, so boundary layer is just adhered to the surface and its thickness is very small. It means delta is very very small in comparison to total length of the plate. So in this case you will be finding, if boundary layer region is very thin, then whatever the streamline which is moving away from the boundary layer region, that will be having actually very small displacement effect. Okay, so displacement of the streamline in the inviscid region will not be significant. Now particularly when your Reynolds number is very high, close to 10 to power 7, in this case we will not be having a fully turbulent, fully laminar region from left to right, but whenever we will be moving along the length of the plate, the point at which my Reynolds number is becoming greater than 3 into 10 to power 6, greater than 3 into 10 to power 6, there I will be having transition from laminar region to turbulent region. So here you can see that in first portion I have shown a very thin boundary layer, and then this trend has actually transformed and it has become bit more thicker. So this is nothing but corresponding to this point I will be having Reynolds number 3 into 10 to power 6. Sorry?
10 into 10 to power 6 to पहले मतलब
only 10.
Next slide. Left side जो Reynolds number 10 power 7.
Yes. No, this is not left side Reynolds number. So this is Reynolds number at the end of the plate, because here length scale you are considering L. So if you calculate local Reynolds number Rex, which is nothing but rho u x by mu. So at starting point x will be 0. So Reynolds number will be 0. When your x will keep on increasing, your local Reynolds number will keep on increasing, and then finally at the end of the plate you have Reynolds number close to 10 to power 7. Okay. So it means that the position where your local Reynolds number is becoming greater than 3 into 10 to power 6, after that you have nothing but a turbulent regime. And in turbulent regime, typically the boundary layer thickness is more in comparison to the boundary layer thickness in the laminar regime. Okay. And another interesting fact is, in the laminar flow you will be having a parabolic velocity profile, whereas in case of turbulent flow velocity profile will not be parabolic. It will be following actually different profiles in different parts of the boundary layer. Okay, so typically very close to the boundary layer it will be following logarithmic, it will be following a linear profile, then after that it will be following a logarithmic profile, and after that it will be following a power law profile. Okay, but in majority of the cases the simplified assumption is we try to consider logarithmic profile because it is prevalent in majority portion of the system. Okay, so that's why that is something different, so detailed understanding of turbulent flow, but the point is nature of velocity profile will be different from that of the nature of the laminar. Yes. One interesting point is that this is the critical Reynolds number at which flow is changing from laminar to turbulent flow. But this critical Reynolds number is actually a very idealistic situation. This idealistic situation will be only true if at your inlet flow is perfectly straight. If you have small perturbation in the flow at the inlet, then before this critical Reynolds number you will be having transition from laminar to turbulent flow. So that's why whenever you do any practical consideration for boundary layer theory, we consider critical Reynolds number to be 5 into 10 to power 5 for a flat plate case. Okay, so ideally it should be 3 into 10 to power 6, but practically we will not be having very perfectly aligned free streams. Free streams will be having certain perturbations whenever these are approaching towards the solid surface. So that's why in practical scenarios critical Reynolds number will be 5 into 10 to power 5. Okay, now the delta is considered as boundary layer thickness. So here you can see in this figure, so at any value of x, whatever this distance is there, this we call delta, and this is nothing but a function of x. So it means whenever your x is increasing, the value of delta is actually also increasing. Okay, so typically if we calculate delta by x in terms of local Reynolds number, it can be approximated as 5y Rex power 1 by 2 for laminar flow and 0.16 by Rex power 1 by 7 for turbulent flow. And for different values of the local Reynolds number, the corresponding boundary layer thickness is actually shown over here. So laminar formulation will be only applicable up to Reynolds number of 10 to power 6, and after that we will be having nothing but a turbulent boundary layer thickness. Okay, so here you can see that when we are moving from laminar to turbulent regime, so we have actually different order of the different values of the boundary layer thickness. Okay, another interesting fact is when this boundary layer theory is applicable, can we apply boundary layer theory for all the values of Reynolds number? Is it applicable for all Reynolds numbers? So what happens basically when your Reynolds number is less than 1000? When your Reynolds number is less than 1000, corresponding to that you will be finding the formation of a very thick boundary layer, and in this thick boundary layer there will be larger deflection of the streamline in the inviscid region. Okay, so if you have very large deflection of streamline in the inviscid region, you will not be experiencing a horizontal parallel streamline, a streamline which is parallel to horizontal direction or parallel to the surface of the plate, but you will be experiencing a curved streamline. Okay, so in case of boundary layer theory, one of the biggest assumption based on which we actually calculate our solution is that we consider that pressure outside the boundary layer is equal to pressure inside the boundary layer, and pressure is actually not varying along the y direction. So it means if I calculate the value of pressure outside boundary layer, that will be same inside the boundary layer. So this type of approximation will be only applicable, will be only true if my streamlines are horizontal. Okay, so if you have a horizontal streamline, then in the top and the bottom portion of the streamline your pressure will be same. But if you have a curved streamline, then what will be happening? You will be having different pressures in between the top and the bottom portion. So this is one of the important things which one should consider while designing even the experimental setups. So in an experimental setup, when you are putting your pressure transducer, you should not put at certain location where your actually streamline is having the curvy nature. Because if streamline is having curvy nature, then at that location, whatever the pressure you will be measuring, that will not be the true representative of uniform pressure at the entire cross section of that particular pipe. Okay, so that will be only possible when your streamline is actually horizontal. Is this point clear? So that is the reason if you have any bend structure or any flow disturbance present in the pipeline, we first allow a longer portion in the downstream to stabilize the flow and the streamline to become straight, and then we put the pressure tap so that we can get a correct estimate of the pressure present in the pipe. But if your streamline is actually bent, then your pressure on either side of the streamline will not be same. Okay, so that is one of the biggest difficulty which we will be experiencing in this scenario. So if I consider my Reynolds number to be less than 1000, for Reynolds number less than 1000, you will be having actually large deformation of the streamline which is in the inviscid region. And because of this large deformation, whatever pressure you are calculating on outside region of the boundary layer and within the boundary layer, that cannot be accurately considered to be equal. So that's why in that particular range, your boundary layer theory will not be applicable. So that's why whenever you apply the boundary layer theory, it is always applicable for Reynolds number greater than 1000. Okay, is this point clear? Second important point is, whenever we apply the boundary layer theory, it is not applicable for the start point. If you see the boundary layer theory approximations, and based on that, if you calculate the wall shear stress, you will be finding at the starting point from boundary layer analysis, your value of shear stress will be infinite. If you have infinite value of shear stress at the starting point, at one point, it means then you cannot move any system in a flow field. Because to generate infinite amount of stress, you have to provide infinite amount of power to overcome that infinite amount of shear stress. So that's why another limitation of boundary layer theory is that it is not applicable for the starting point. Whatever the starting tip is there, it is applicable after some very initial starting portion. Okay, so that's why you should know very clearly what are the limitations of boundary layer theory. So this is not applicable for Reynolds number less than 1000, and this is not applicable for the starting tip of a system. Okay, now analysis of boundary layer theories is actually very simple for when we talk about the streamline bodies, because in case of streamline bodies, our profile of the boundary layer is actually very smooth. But if we consider the blunt bodies like cylinders, spheres, there what happens, so here you can see the Reynolds number now is calculated based on the diameter of this body as a length scale. So that's why you are writing it as nothing but rho ud by mu. Okay. So in this particular case, when Reynolds number is 10 to power 5, I can represent my streamlines in two ways. So one way is I am drawing the smooth streamline structure over here. Okay. And in this smooth symmetric streamline structure, you can see this black colored dashed line is nothing but I am calling it as a boundary layer region. Okay, and so whenever we are not considering the practical difficulties, we can just simply assume that okay, my boundary layer regime will be something like this. Then I will be having formation of a very nice wake structure at the trailing edge, and then my streamline, whatever I will be having pressure loss in this region. So in this region, this is a converging region. So here what will be happening? I will be having pressure loss because flow will be accelerating and pressure, some part of the pressure energy will be converted into kinetic energy. But after this point, my flow is now diverging. So here velocity will slow down and pressure will increase. So I will be having some pressure recovery. So in an idealistic system, one can simply assume that I will be having very smooth streamline structure, and whatever pressure loss I am having in the upstream section, same pressure gain I will be having in the downstream section, and I will be having a well behaved wake structure. Okay, but this is something which does not happen in reality. Okay, so in reality, if you consider the same Reynolds number, you will be finding that your streamline will be only passing up to the front portion like this, and after that in the rearward portion you are not having a clearly defined boundary layer. So you are having a very thick boundary layer portion. Okay, and in this particular thick boundary layer portion, you will be getting that whatever the streamline you are finding just passing through this boundary layer region, that particular streamline is actually not bending too much. If it is not bending too much, I will not be having pressure recovery here. Okay, so pressure recovery will not be here, and this type of situation is nothing but called as flow separation. So what is happening? Flow is actually separating or leaving from the solid surface. It is not attaching to the solid surface. Okay, and this flow separation initially for very small Reynolds numbers, this almost start at the stagnation point at the rear, and the value of this the location of this flow separation actually keep on shifting towards the upstream direction upon increase of the Reynolds number in the laminar regime, and after that whenever we enter in the turbulent regime, then again it shifts towards the rearward direction. Is this one clear? So how it shifts, that in detail we will be seeing, but one simple point is that I will not be having a very smooth structure. So because of this, boundary layer approximation will be only applicable up to the point where actually flow is attached to the surface. But when flow is away from the surface, we don't have attached flow situation and a well-defined boundary layer, and we have formation of large number of vorticity. So here you can see a large number of vertical structures are actually present in the flow. So these are called as actually very chaotic wake structure. So in this chaotic wake structure, your calculation of pressure and velocity field cannot be obtained from the boundary layer theory. Okay, so here again then we have actually experimental, we have to again rely on the experimental or numerical techniques. Okay.
सर इसमें लोकल नंबर निकालने के लिए हम लेंथ स्केल क्या करते हैं?
For this type of situation, because we don't have very large length portion, so that's why we just try to calculate this single Reynolds number, which is based on the diameter scale of this.
तो हर जगह का रेनॉल्ड नंबर सेम.
Yes, means Reynolds number of course will be different, but what we are saying is flow velocity will be different, but what we are saying is we are characterizing the entire flow field based on the free stream Reynolds number. Okay, and this free stream Reynolds number is calculated based on this particular length scale, which is equivalent to diameter. Okay, so local Reynolds number you will be finding will not influence your this region over here. Okay, so here in when you will be defining the boundary layer thickness, that you will be actually defining simply based on other parameters without non-dimensionalizing it. Okay. So whenever we solve the boundary layer approximation, first let us simply talk about a two-dimensional flow over a flat plate. Okay. So this is a plate and over this flow is happening. So you will be having formation of a boundary layer region here. So if you have to solve this type of two-dimensional situation, I can fix my x coordinate system in this direction and y coordinate system in this direction, and this is my free stream velocity. Okay, so in this case my flow field is two-dimensional and incompressible and steady. So I will be having one continuity equation, and then I will be having two momentum equations, x and y momentum equation. But what I can do now, I can make certain approximations. I can say that if my boundary layer is thin, and also because of the thin boundary layer, there will not be much displacement of the streamline. If there is not much displacement of the streamline, my streamlines will be almost horizontal and all the velocities will be actually dominant only in the x direction. Okay, because if your streamline is having significant displacement, then this will be your velocity vector, which will be having significant horizontal and vertical components. But if your streamline is close to horizontal, then your velocity field will be majorly dominant in the x direction. So that's why my v will be very small in comparison to u. But if you consider your thick boundary layer region, then this approximation cannot be applied. So that is the reason that boundary layer theory is applicable for thin regions which is having the value of Reynolds number greater than 1000. Okay. Then another important point is, if you see the gradient of velocity in x direction and gradient of velocity in y direction. So what happens in a two-dimensional flow field? In a two-dimensional flow field, if at different x locations you will be drawing the velocity profile, that will be something like this. Okay, so it means this velocity profile is having some self-similar nature. Okay, so it means if you non-dimensionalize this distance, so this is nothing but y direction, if you non-dimensionalize this y direction with delta, boundary layer thickness y by delta, and then if you non-dimensionalize velocity on abscissa with u by capital U, you will be finding a single velocity profile for all the locations. So velocity of all the locations will be collapsing on a single profile. Okay, particularly in laminar flow regime. And even in turbulent regime also there will be similarity, but fluctuations will cause some other issues. That is something which we are not going to discuss at the moment. Okay, so another important point is, because you are saying that you don't have you have this self-similar behavior, so it means when you are moving along the x direction, there is not much change in the velocity. On contrary, if you see y direction, in y direction immediately outside the boundary layer you have capital U velocity, and just close to the surface you have zero velocity. So it means you have, and moreover the thickness of this boundary layer delta, that is very very small in comparison to length of the plane. So that's why in case of lengthwise direction x-axis, we have actually larger length portion along which variation of velocity is small, but in the vertical direction we have very small boundary layer region in which actually variation of velocity is strong. So that's why del u by del x variation of velocity in x direction, particularly the x direction velocity, is very small in comparison to variation of velocity in y direction. Okay, and if you talk about v velocity, here also actually you can simply say the similar thing. Okay, then now another important point is, if your v velocity is very very small, then it can be nearly approximated close to 0. Okay, it is negligible. So if v velocity you approximate close to 0, so all these gradients del v by del x is small, this will be close to 0. V is small, this will be 0. These gradients 0. So what you are getting? You are getting that from the second momentum equation, you are getting that del p by del y is nearly equal to 0. So if your del p by del y is 0, it means your pressure is only a function of x. So it means if you move in y direction, you go to any value of y, you will not be having change in pressure. So simply if you calculate pressure outside the boundary layer region, same pressure will be applicable for within the boundary layer region also. So that is something which is the advantage we will be taking, and because of this, del p by del x can be written as dp by dx. And now if I solve this x momentum equation outside the boundary layer, what will be outside the boundary layer? Del u by del x is already small, so here del u by del x is small, so this can be substituted simply equal to 0, and outside boundary layer del u by del y is also equal to 0, because outside boundary layer even u velocity is uniform. So this will be also 0 and these will be also 0. So ultimately, no, these will not be 0, particularly this will be 0 and this will be 0, but del u by del x will not be 0, because ultimately whenever you are moving in the x direction, okay, so if you have pressure gradient present from this point to this point, what will be happening? There will be change in your velocity value in the x direction. So that's why outside boundary layer, what I can write, in place of velocity, my velocity will be capital U, okay, and because velocity is nothing but free stream velocity, and at the same point of time this free stream velocity will be nothing but function of x. How it can happen? So maybe for flat plate it may not appear to you that outside boundary layer velocity is changing, but if you take a wedge section like this, if you take a wedge section like this, then what will be happening? Your flow streamline is coming like this and then it is bending. Okay, so because of this bending, here I will be having nothing but acceleration of the flow. So because of the acceleration of the flow, my velocity value will be actually changing as I am moving in the x direction. So that's why my free stream velocity will be nothing but, at this point it is u, but whenever I am moving towards the solid surface, the value of u is actually changing as I am coming closer to the surface. So this u is nothing but a function of x. Is this point clear? All are clear with this idea? So u is not constant, it can be a variable with x direction only. So that's why in this x momentum equation, outside boundary layer, small u I can replace with capital U, but capital U can vary in x direction but not in y direction. Y direction at a particular x it will be remaining constant. So that's why the x momentum equation outside boundary layer will be giving me that del p by del x, which can be simply written as dp by dx minus of rho u into du by dx. Is this point clear? And is this point clear? And second point is, from the continuity equation you can see that your del u by del x plus del v by del y is equal to 0. So if you do order of magnitude analysis, this will be capital U by L and this will be U by L of the order of V by delta. Okay, so V will be nothing but delta U by L. This is also when delta by L is actually very, very small than 1. So that is the reason earlier I wrote that V is very small in comparison to. Okay, and this can also be seen in terms of the streamline which I have explained you earlier. So once I invoke all these assumptions, what will be happening? I will be getting some simplified set of equations. What are these simplified set of equations? A continuity equation. In terms of momentum equation, from the y momentum equation, I was having this only term del p by del y equal to 0. So it means y momentum equation is completely gone. So I will be having only x momentum equation. So in x momentum equation, I have u into del u by del x plus v into del u by del y, and this dp by dx I have replaced with capital U into du by dx. Okay, and this du by dx can be simply calculated by applying the Bernoulli equation at different locations in outside the boundary layer, because outside the boundary layer my flow is inviscid, so I can apply their Bernoulli equation. Okay, and then I will be having, of course, viscous term which is written in terms of del tau by del y over here, and if flow is laminar, then it will be simply equal to mu times del u by del y. If flow is turbulent, then it will be mu times del u by del y minus rho u dash into v dash. What are u dash, v dash? These are the fluctuating component which will be leading to additional stresses in the flow, which are called as Reynolds stresses. Is this one clear? And u is a function of? No, this is not outside boundary layer, this is inside boundary layer. Yes. This is also inside boundary layer. Only this particular term I can calculate from outside boundary layer, because capital U is applicable outside the boundary layer. Is this one clear? All are clear with this idea? So this is just a revision, because already you might have studied boundary layer theory in your BTech as well as the advanced fluid mechanics course. Okay, so this is the, I think, only a revision part. Then at y equal to 0, what will be the boundary condition? If you have a solid wall, then impermeable and no slip boundary condition, and at the outer location when y is equal to delta x, then your velocity is nothing but equal to free stream velocity, but this is a function of x. So at different values of x, your free stream velocity is actually changing. Okay. Then I have given the second approach that I will not discuss now, but what I will do, I will give you some small idea about how flow behaves if you have flow past a sphere. Okay, so this is the situation when your Reynolds number is equal to 1, and in this figure flow is from right to left. So please note this point. Here flow direction is from right to left, and these are the different streamlines which are actually plotted over here. Okay, so you can see when your Reynolds number is close to 1, then you have almost a symmetric nature of the streamline, which is nothing but following a creeping flow situation. Okay, once your Reynolds number is increasing, going close to 10, then you will be finding that in this zone and in this zone curvature is different. So it means whatever the loss of pressure here we don't have the same gain of pressure in the backward. Is this point clear? So in this portion we have this difference. And when my Reynolds number has increased to 50, in that case streamline is actually leaving now the surface very early. So at this point streamline is just leaving the surface, and then I am having formation of a vertical structure below this streamline in the rearward portion of this particular flow. Okay, and upon further increase of Reynolds number, what is happening? This streamline is leaving even early, and this vertical structure is actually growing in size. So it means I have the formation of a wake, and the strength of this wake and its extent is actually increasing when we are increasing the. Okay, and this is typically the vorticity contours for flow over a sphere. So in case of vorticity, you can see when your Reynolds number is close to 1, then this is your vorticity profile, but in upstream and downstream portion your vorticity field is actually asymmetric. Okay, when your Reynolds number is equal to 10, then your vorticity field is being diffused towards the downstream direction. So here you can see this portion has actually shifted more towards the downstream direction. So it means that whatever the vorticity generation is happening at the front portion, that is actually being extended to the downstream direction, and this is being extended away from the surface. So close to the surface we will be having some formation of other different type of small vertical structures. Okay, and this is the typical representation of dimensionless vorticity at the surface of a sphere. So in terms of dimensionless vorticity, you can see that this is angle. So when you have angle 0 and angle 180 degree, so corresponding to Reynolds number equal to 1, this is the line. So vorticity is not having any change, but in this case when Reynolds number is 10, then vorticity near the rear portion is actually becoming negative, and when your Reynolds number is further increasing, then your change in sign of the vorticity at the surface is actually strong, which is nothing but because of the formation of these vertical rolls just behind the rearward surface. Okay, and further increase of Reynolds number will be giving you very strong vorticity in the upstream portion, and then behind you will be having actually very negative vorticity with strong magnitude. One simple point you can observe is that the peak point of vorticity is just at the middle for Reynolds number equal to 1. This peak point has shifted towards the upstream direction when you are increasing your it has shifted towards the upstream direction when you are increasing your Reynolds number. So upon increase of Reynolds number, the maximum magnitude of the vorticity at the surface is increasing. At the same point of time, its peak point is actually shifting towards the rearward direction. So you have the occurrence of highest vorticity in the lower angle positions. Okay, is this point clear? So today we will be having very short lecture, and we will be now closing this lecture, and tomorrow we will discuss further.